morning, everyone. Welcome to today's presentation. Let's get right to it. So the focus of today's presentation, as Lisa mentioned, we're going to give you a quick overview of the safe design and the implementation of IMRs, industrial mobile robots. And we're going to give you a little update on a few industry standards that provide guidance for the safe design and the construction of these types of vehicles, and some of their similarities and some of their differences. We'll review some of this background and a couple different standards, the revised version of the ITSDF B56.5 standard for AGVs, and a developing standard for autonomous mobile robots and the RIA R1508. The presentation should take about 45, 50 minutes, and we'll leave some time at the end for questions. And as Lisa mentioned, you can type those questions into the Q&A as it progresses, and then we will cover those at the end. So there's a lot of common technology behind both AGVs and IMRs. However, there are a few key differences that require the application of the guidance that are found in these C-type standards we're going to discuss a little bit today. Each of these mobile platforms, it is imperative that we think about designing, constructing, and implementing them safely. And to do that, we need to understand these key differences. One thing that is common, however, to both AGVs and AMRs is that we'll follow a process of thinking about how to design, construct, and implement them safely throughout their life cycle. We talk about the 6 steps to any safe machine, and it applies certainly to these types of vehicles. Typically, we have to look to the laws, the regulations, and the standards that help support those laws and regulations. And this is where we find our benchmark. This is where we find the target that we're trying to hit when we're working with these types of platforms. Once we understand what we need to do, we're going to conduct a risk assessment to identify all those tasks performed in and around the environment of the platform, and it's the affected personnel that may come in contact with the platform as it's moving, stationary, doing its work. The information from the risk assessment leads us to the risk reduction. How are we going to handle these interactions in a safe way? So we talk about safe design measures. We talk about technical protective measures, implementing safety functions to controlling the movement and the hazardous motion. And in the end, we want to inform users of the devices, how to implement them safely, any awareness measures, horns, beacons, signage, training, those types of things that also add to the overall risk reduction of the safe implementation of such platforms. And in the end, we want to evaluate to make sure that we've achieved our aims that we set forth in the risk assessment. And then we can place the system or the platform on the market, and over its lifetime that we can use it safely in the manner as intended. So let's take a look at North America. What are the laws and regulations, and how do we pull these together to support the use of the standards as the way we do? OSHA is our legal framework in North America, specifically in the United States, and we look to the Code of Federal Regulations under 1910-12, where we'll find the General Duty Clause that puts the onus of a safe work environment on the employer, right? Really, the end user is responsible for providing a safe work environment. Therefore, we need to find information of how to do this properly. And we find that information, or the guidance of how to design and build and construct these types of machines, or any machines and platforms, through consensus standards. So we'll talk about a couple of these consensus standards today that are both happen to be ANSI standards, so American National Standards Institute. So the the developing organizations who have taken the time to organize and develop these standards under the ANSI framework can publish these as ANSI standards. One thing to keep in mind that ANSI standards are third-party consensus. They're voluntary standards. They're not cited necessarily by regulatory requirements. There's no requirement, but they do provide a very well thought out, state-of-the-art, industry-accepted methodology for doing this properly. And therefore, by complying with the tenets found in these consensus standards, you can go a long way to ensure that you've met the requirements set forth in OSHA. A couple standards we're going to talk about today. A new developing ANSI RIA standard, the R1508. It is under development. It's for industrial mobile robot safety. So we'll talk about what's new in that standard. And we'll talk about the newly released ANSI ITSDF, the B56.5. This is for AGVs, safety standards, automatic industrial guided vehicles. And we will take a look at that standard a little bit and talk about its application. So what makes automated guided vehicles, AGVs, different from industrial mobile robots? So the main difference is how they follow their path through any given space, right? Most AGVs follow predetermined paths. That means they go from A to B in a predetermined way, and they are guided by their navigation system along that path. And AMRs, on the other hand, are autonomous in nature, which means that they can determine their own path. They can use AI, they can use path planning, they can use other implementations of technology to help them navigate through a facility, and therefore can find the most efficient route, considering other influences to the space like people or block dialways or even other AMRs operating in the area. So they'll follow suggested paths if they exist, but they do have the freedom to find their own way through the facility to get from A to B. So the difference leads to differing methodologies for ensuring safe operation. And therefore, we want to really look at how we might go about doing that. So let's talk about traditional automated guided vehicles covered by the B56.5 standard. This standard has seen numerous revisions over the years, and the current edition, the 2019, that was just released, very similar in the past, contains the guidance for both the user, the end user. This is found in part 2 of the standard. Or if you're the system supplier or the manufacturer, you'll find information pertaining to your activities in part 3 of the standard. The standard does provide for the safety guidelines for the construction and the implementation of these AGVs. And also under consideration is manned vehicles that have become unmanned and maybe redeployed in a semi-automatic manual mode. So it's also something to consider, but that's the general scope of the B56.5. So let's take a little look about path following for AGVs. You know, typically an AGV, again, has a predetermined path from A to B. When we look at an autonomous mobile robot, however, it may take a predetermined path, but it may have path planning. It may take other routes to get through the facility from A to B. Therefore, it can leave the predetermined path and find its own way through its navigation. An AGV also, when it determines that there is an obstacle within the path, this could be an object, could be a person, it comes to a halt, right? Once the object is removed, it may continue along its path. There are requirements in the standard for how this has to function, how it has to stop, how it has to sense, the speeds, the object detection capabilities of the devices on the platform. This is all covered in the standard on how to go about doing that. Some AGCs or smaller versions and even AGVs can either slow down and then come to a stop when the object's detected again and move on as necessary. Autonomous mobile robot, however, when it detects an object, it can use its navigational algorithms and facilities to find another path through the plant. Right? This is a typical difference between these types of navigational methodologies found in both platforms. If we look at traditional AGVs, they may be single direction, they may be bidirectional, but they follow a path and therefore they need some sort of object detection capability within that path so that they can determine if there's an obstacle obstructing their way. They can change speeds. They can look around corners as they turn, following the path. And typically, 2D LiDAR is a very typical approach to doing this object detection. You can also use bumpers, but there are requirements for using the bumpers, and the vehicle still needs to stop in a predetermined way before it comes in contact with the object, even using bumpers. So let's take a look at industrial mobile robots then. This is the RIA 1508. This is a new work item. This is under development by the RIA. It is being developed in a couple different stages, and they are seeking input and participation on this committee from both robotic and AGV experts, as well as end users. It's always good to have a lot of points of view when ensuring that the standard's developed, thinking about all of the technology available, as well as tried and true methodologies that come from industry experts who have already worked with these types of platforms in the past. SIC is a full committee member. We are facilitating and helping to write this standard. And I would suggest, if you are interested, that you get in contact with the RIA and see about joining this committee if you are so interested. Currently, as I mentioned, this is under development. So a target release for part one, this will be for suppliers. These will be for manufacturers of these types of mobile robots, so these mobile platforms. They still are looking to try to release this next year, about mid-year. It is a lot of work. There's a lot going on in really getting a lot of the definition and the scope for the manufacturers. A lot of these platforms are already being manufactured, and therefore there is a lot of industry expertise on the standard and on the committee who are helping to implement this. And they're bringing a lot of real-world information and background to the standard committee. Part two is for the integrators. The integrators, these will be the organizations and the groups that will be required to implement these devices into the real-world applications and deploy fleets of these, if you will, and the systems that support the fleets for navigation throughout the facility. That will begin shortly, but the standard writing committee hasn't gotten to that section yet. In the ISO world, this is all that's required for development of the standard. Therefore, end user information will begin development shortly, but because in North America, and specifically in the US, we are an end user, as I mentioned, the responsibility is on the end user. Therefore, we need additional information in the standard to support the end user and the safe implementation and overall lifecycle management of such systems. So that'll also begin development. Ongoing issues with defining the scope. We'll go through this in a little bit of detail here. there's a lot more to just saying I have a platform and I'm going to attach something to the top, or I have an autonomous platform. There's other things. There's software, there's AI, there's transportation information. There's what is attached to the platform itself. Is it a robot? Is it an articulated robot? Is it dynamic? Is the attachment in motion performing some function while the base platform is stationary, or is it moving? These are all very interesting topics that take a lot of thought to think through properly, and therefore the standard writing committee is struggling and wrestling with these topics as we speak, right? So let's take a look at the current definitions of the scope of this document. I think this is really important. When talking about the requirements for industrial mobile robots, the key word here is industrial. These are being developed, the standard is being developed to give guidance to industrial applications, not in the public space. We expect these vehicles, platforms to operate within spaces in an industrial environment where most of the people they come in contact with are trained, they understand the operation of the systems and the platforms within the industrial space, and therefore certain risks and certain tasks and hazards are more appropriate for this type of application. No public access. Mobile. Now this does refer to ground-based mobility and not to water or airborne type of vehicles. So if it's mounted on rails, if it's in water, or it's airborne, it will not be covered by this standard. However, if it's mobile in an outdoor application, there'll be some additional environmental requirements that'll have to be considered both by the manufacturer, designer, implementer of a platform or mobile robot, as well as the integrator or the application that it's for its intended use. The robot, as we talk about the platform, actually applies to 3 possible constructions, and we'll talk about these in detail, but it could be the industrial manipulator attached to a mobile base, which may or may not be autonomous, the mobile base that has a degree of autonomy greater than your traditional AGV, with or without anything attached to the base, and then the same unit with the mobile base and a robotic articulated arm with a degree of autonomy and is capable of operating dynamically. So let's take a look at some of the terminology that's being defined underneath the development of the standard. So as I mentioned, an autonomous mobile robot is a mobile platform that is autonomous. That means it has the ability to navigate using obstacle avoidance, trajectory planning, rather than a predefined path. So what is obstacle avoidance? So preventing interference such as approach, contact with objects, whether it's a fixed object or a moving object like other AMRs and or persons in the area, detecting them with sensors and adjusting their trajectory. So collision avoidance then is a safety function, right? We're reducing risk with this application. So the safety functions take a predetermined action. Do I slow down? Do I stop? Do I take another path? Do I steer around to avoid collision, right? This is a safety function. Therefore, it relies on the safe operation of the control system and the sensors, giving the sensory input to the object detection. So there will be requirements around the safety functions and the implementation of the safety functions on a platform. The trajectory planning, right? So again, trajectory planning is about planning the path with time as the parameter. How do I get from A to B? What's the quickest way to get from A to B where I avoid obstacles and therefore can be the most productive and efficient in moving through the facility. Now, path planning is this iterative process of using different ways of computing an obstacle-free path. This can be AI-supported, cloud-based, could be map-based, also information taken from other AMRs operating in the same facility. This is a fleet, if you will, and fleet management throughout the space between any two locations that any given platform needs to navigate in. So let's take a look about the qualifications of the standard as it addresses the different types of AMRs that will be covered and won't be covered by the standard. So if we think about, is this an industrial application? As I mentioned, the standard is governing industrial. So if this is a public space, this standard will not be applicable. If it is a mobile platform, if it isn't a mobile platform and it's stationary, okay, then it has a manipulator of 3 or more axes. Well, we know that there's a standard for that, and if it is, then that's an industrial robot system. That's covered under the R1506. So it will not be covered by this standard. If it does have navigation, but it's manual, and it does not have a manipulator, then it won't be covered. However, if it is guided as an AGV, okay, it is a mobile platform, but again, if it doesn't have an attachment, then this is covered by the AGV standard. So it is a guided vehicle. We have a standard for that. We know that's the B56.5, so we're covered. If it has some other type attachment as well, potentially, regardless of the attachment, if it's still guided, it's still AGV. If the navigation, however, is autonomous, it is an AMR, an autonomous mobile robot. But let's take a look at the different types of attachments. If we have no attachment, this is a type A. So the standard is defining the requirements for a type A mobile platform. If it has another type of attachment, this is a type B industrial mobile robot. Could be a conveyor, could be bins, could be a cart. Could be a forklift. If it, however, has a 3+ axis mobile manipulator, this will be considered a type C. If we have a guided vehicle, mobile platform, and we have an attachment type as a manipulator, this will also be considered by the standard as a type C mobile manipulator. When we think about monitoring for these types of platforms, we need to think about monitored space. These units are moving and they're going to add some dynamic, potentially add some dynamic applications. Again, as I mentioned, we have to think about, traditionally AGVs have thought about 2D space. Just need to see the line of sight and the direction of travel to ensure obstacles are detected and that they're not impacted or we have the collision avoidance with objects. Once we start to put manipulators and other types of attachments to the tops of these platforms, we now have to consider a potential 3D space, things above the line of sight or the detection at the floor level of objects in the path of travel. So we have to think about that space and the 2D space. Now the monitoring system consists of components that are not necessarily safety rated. There will be requirements in the standard to address the level of safety required based on the risk. This is what the risk assessment will help you define. And again, there is a new standard, IEC 62998, that allows you to implement sensors and safe applications. If you're interested, you should take a look at the standards, the newly published standard. And it gives guidance for safety-related sensor systems, specifically for these types of applications. The monitored space, when it can change dynamically, we need to think about, again, things going on at different types of, during the motion, we may have the actual articulation or the attachment doing something, manipulating, moving material, and that can be happening dynamically while the platform's in motion. So there's a lot of other things to consider when we think about safe sensing of objects. So let's take a real quick look at the standardization as it's starting to develop scope around the space. So if we think about in the AGV standard, it covers the space, restricted space, and operating space, and it has all the requirements defined in the standard, which is very well thought out and traditionally has been understood very clearly about how to define clearances between immovable objects and the path of the AGV, and so on and so forth. Taking that thinking that's been available to us for quite a few years, as in the AGV world, now we have these more dynamic autonomous platforms. So how will they know about these clearances to other objects and be able to stop and ensure safe space is allowed for safe interaction with humans or other personnel and or objects within the space? So thinking through this, the Standardization Committee has started to define some of these methodologies for thinking about the operating space that these platforms will run. A segmented space within the free space is a zone, right? We'll have hazard zones. These are spaces in and around a machine which in an individual can be exposed to a hazard. So it makes sense if you're in this area, there are hazards associated with being in this area. For an IMR, this will include all the spaces of inadequate clearance. As I mentioned, there are clearance requirements in the AGV standard. Some of those same clearance requirements, I'm sure, will find its way into the standard. And there will be minimums of clearance around hazards. Some of those will be defined as keep-out zones, right? A zone excluded from the free space. Free space will be allowed, which an IMR can pass plan freely. There are not expected to be any fixed objects. There may be some dynamic objects or other movements in the area, but in this free space, the IMR is free to navigate. But once it goes into an area where it's absolutely restricted, these will be keep-out zones. There just won't be enough clearance. It's already been predetermined. There's no need for the IMR or the AMR to move into the space. So this will be defined as keep-out spaces, keep-out zones. And that brings us to base footprint. So the two-dimensional projection of the IMR in the working space will become its base footprint. So what is special, or what do we need to consider when we think about the base footprint? So when we think about the IMR type A, just the mobile platform, a simple or smart implementation, or if you will, a non-smart implementation, really can navigate and can object detect, but this is like your Roomba, you know, iVacuum running around. It really doesn't have a good picture of what it sees or what the space is. It's just bumping its way around, and therefore needs a little bit more space around it because it's really not navigating with any exactness. It is just operating in free space, has safe algorithms to do that, but it's going to need a little bit more footprint. However, a type A IMR, which is more advanced, is going to have advanced navigation. It's going to have more information about its space that it's operating in. This could be a map. This could be predetermined or memorized locations of objects, or combinations of those. This allows the device to have a little bit more understanding about those restricted areas around it. So if we have a type C with a manipulator, you can quickly understand that if I'm not navigating in a really defined, really well understood space, I'm going to need more room to ensure that the clearances around the manipulator are going to be sufficient enough to operate safely. If I'm going to have a more advanced, and I understand where I'm operating, I have these maps, I have this extra information, and I have more navigational ability, I can now also understand a safe operational space or restricted space, if you will, for the manipulator to ensure that it operates safely. Whether that's dynamic or it's fixed, if the platform's fixed and the manipulator is moving, I can then only concern myself with that actual movement of the manipulator while the platform's fixed. But again, the more advanced detection capabilities of the platform will give it a little more leeway in how much clearance is going to be required around the IMR. So in the end, that's a design consideration when we think about dumb versus smart, if you will. So that smart spatial recognition and understanding what's in the space is necessary for safe navigation throughout these zones. So when we think about the zones, right, the definition of the space, it might be something that looks like this. This is something that gives definition to the free space you see here in the green. This is the space where the IMR is free to navigate within its autonomy and its algorithms for navigation, whether that's AI, it's cloud-based, it's map-based, learning, regardless, this is the free space that it is allowed to operate in. The keep out zone, this will be areas of other automation or other areas within the facility that are off limits. And there's no reason for the IMRs to operate in these spaces, so these can be defined and restricted. Hazard zones then are when the IMR may contact other objects, both other AMRs and or objects such as people, and there's some sort of restriction. And that restriction has to be thought of a little differently because maybe it's a lack of egress. Maybe it's a storage area where the AMRs is either retrieving loads or other trucks or other picking up material, dropping off material, interfacing to a conveyor, wherever there might be some interaction where there will be some spatial requirement for ensuring that people are not injured in these areas where they may come in contact, and there will be some sort of space restriction. So this is the type of environment planning and definitions of the scope that's ongoing within the standard. So lastly, a little bit about SICK. We provide these, as I mentioned, there's 6 steps that we follow in a logical path whenever we're providing our consulting services and we're thinking about supporting our customers in the application of the sensing products and or their safe implementation on these types of platforms. As I mentioned, we understand the laws and we understand and support the development of these consensus standards. So we help bring this knowledge to the industry, to the market, and to our customers to help them do this in a proper way. And we do that through providing consulting and services and risk assessments and the safe design of our products into these types of platforms. We can support you through that worldwide. And therefore, we can ensure that our products are used in a manner intended the way that the requirements in the standard are giving guidance to. So with that, are there any questions? Looking at the Q&A, I Don't see any questions. With that, I believe we're done. Lisa, is there anything else you have?
No, thank you, Mark. Again, a recording of this webinar will be shared via email after this webinar, as well as on our website. So thank you, Mark.
All right. Thank you, everyone, for your time. Have a good day.